Hello everyone, welcome back to another Civi 398 example tutorial. First of all, congratulations on completing all of the main topics of continuum mechanics. This is a very difficult course, but you guys have done so well, and I'm so proud of each and every one of you, even if you think that my videos are a little bit too easy. Alright, to wrap up the course, we are going to discuss the finite element software ABAQUS. Unfortunately, the finite element theory, so the theory within the software, it's actually really complex and outside the scope of the course. So we're not actually going to get into the theory of the finite element method. However, many of the method's fundamentals are actually based on what we have learned in continuum mechanics. So as we're creating our models here in ABAQUS, you guys will see a lot of familiar terminology that you guys have learned in this course. Now, some of you are going to go, well, Clayton, why do I need ABAQUS? And the answer is, well, you probably don't. ABAQUS is a very complex finite element program that is more suited for graduate students and research purposes. And you're saying, oh, well, if I don't need it, why would I bother learning it? Well, that's a great question because even though ABAQUS itself is a finite element program suited for research and graduate students, many of the actual engineering softwares that you guys will see as practicing engineers is actually based on the finite element method. Very popular ones include SAP and ETAB, so those are structural design software where I can design beams and columns and slabs, everything like that. That's actually based on the finite element method. So even though we're teaching you guys ABAQUS, the goal here isn't to teach you ABAQUS specifically, it's to teach you how to create a finite element model, because if you guys know what to look for in a finite element model, when you guys transition to other programs, you guys are going to be good to go. Now, in this tutorial, which I call tutorial 1, we're going to start off very simple and solve a nice cantilever beam problem. When I show you guys the cantilever beam, you guys are going to go, Clayton, we don't even need ABAQUS. I can solve this using all the theory and Mathematica code I created throughout the course. And you guys are correct. You absolutely can. But we want to try and start off slow and say, all right, how good of a job does ABAQUS do at approximating these solutions? All right, guys, let's take a look at our beam. Alrighty guys, here is our beam. As you guys can see, a nice cantilever beam. We have a concentrated point load at the end of 200 kilonewtons, and we have some material properties of this beam. So when we're getting into these finite element models, they can become very, very complex. But in this case, we're keeping it, again, really simple just to show you guys how to use the program, what to look out for, and stuff like that. So our material properties, we kept this as a nice linear elastic isotropic material. So we need two parameters to define that property, of course. We talked about this, which is the Young's modulus E, which we have defined as 20,000 MPa, and the Poisson's ratio nu, which I have listed as 0.2. Now, one of the things that we're going to also have to keep in mind when we're defining these models is we're going to have to keep a good track of the geometry of this beam. So if we look, we can see that our beam is 2 meters long and has a height of 0.25 meters. Another property, as you guys are going to see, that we're going to need is that in-plane thickness. So of course we have our beam in 2 dimensions, but beams are actually 3 dimensions. They have that component going into the page. However, we have that listed as 1 meter. So now that we both know the material properties and the geometric properties, in addition to the loading and boundary conditions of this beam, we can solve for it or approximate it in ABAQUS. So we're going to jump on over to ABAQUS and I'm going to show you guys how to do this. Alright guys, so when you first install ABAQUS and open it up, you guys should have this screen. As many of you guys will see, the hardest part of ABAQUS is actually installing the sucker. Sometimes it just does not want to work. But if it does work and you guys open it up and you guys have this screen, you guys are good to go. So this is basically the start screen of ABAQUS, and from there we can start creating our model. So the first thing that it always gives you is this nice big box, and it says start session. Well, I just exit out of that. We don't really need to do anything there. And right here is my actual model. Now, as we can see, the screen, of course, is blank because we haven't defined anything. We haven't created anything like that. So the first thing that we want to do is we're going to want to save our model. So we're going to go File, and we can go, all right, we want to save this as. And here's something very important. When we install ABAQUS, it's going to ask you where you want your ABAQUS files, and typically it'll default to your temporary folders. So if you guys ever want to find an ABAQUS folder and you just saved it without really defining where you guys want to save it, it'll be in your temporary folder, which can sometimes be a pain in the ass. So of course I want to try and throw it into a folder in which I can find it. Now I have too many folders, I have no idea what to do. So here I have a place and I want to save my model. So I'm just going to put it as a cantilever beam. And as we can see, the model will have an extension .cae. So I'm going to save it and I'm going to be good to go. So every time I save my model, it's going to save to that file where I've now defined the path of that file. The second thing I want to tell you guys, and this is kind of a sneaky one with ABAQUS, is when you guys create your model, again, all of the information of the model is going to be stored here in this CAE file. However, once you guys run the analysis results will be stored in a separate file. And if you guys don't define where that separate file is going to be located after, of course, it's going to throw it right back into the temporary folder. So now instead of going save as for our actual thing, we also want to set the work directory. What this means is that anything that we come out of with this model, so let's say I have my model, I run an analysis, and I have an analysis file. Well, as we can see right now, it's going to save that analysis file back into the temporary, but I want to try and keep all my files together. So I'm going to put this in the exact same place. And let me just expand this here so I can actually read what's going on. I'm going to put this in the same place as my CAE file. So all of my ABAQUS files are linked together. So let's put this, good to go. All right, so that's going to be the hardest part. Is a lot of people run an analysis and go, Clayton, where the hell is my actual analysis file? It just disappeared on me. Well, it's probably in your temporary folder because you need to define both where you're going to save the model as well as where do you want to send the outputs of the model. All right, so that's kind of the first little tidbit. I'm not going to go over that every model because, of course, once you guys know it once, you guys are going to know it forever. So now we're going to get into the actual creating the model part of this tutorial. So when we get to ABAQUS, it's really overwhelming at first. We have all these buttons. We have this model tree on the side with a lot of different options. It's hard to tell what exactly we want to do. So when we're creating these models, the best thing I like to do is look at this little module tab. So right now we are in the part module. Now, the way I create my models is I'm just going to go through each one of these. So we can see we start with part, then we go to property, then assembly, step, interaction, load, mesh, optimization. You guys don't need to worry about that one. And finally, we finish with job. And job basically means run the analysis. So all we're going to do is we're going to go through each one of these until we reach job. By the time we reach the job module, we should be good to go to submit our analysis. So as we can see, by default, ABAQUS starts us in the part module. Now, what the part module is this is where we create the parts of our model. Now, it's kind of hard to tell because we're only dealing with one beam, but many models, of course, have many parts. You guys know that I do masonry, so of course, each block would be a separate part. So in this module right here, we're basically creating all of the individual parts that we're going to use within our model. Think of this like Lego. Of course, when we're building Lego, our goal is to complete that whole set, but to do that, we use a bunch of little tiny pieces. Now, this part module right here, this is creating those little tiny pieces. This is not assembling them, but this is just creating all of those little pieces. So there's two ways to do this. We have buttons on the side right here that says create part. So as we can see, a nice big button, or we have our model tree right here. So if I see that the first one says parts and I double click it, it'll say, do you want to create a part? Well, yes, I do. And when we create the part, as we can see, we have a couple of options. The first one is the name. Of course, we only have one part, so it's not going to be too hard to get it lost, but it's good, a good convention to name whatever part you want to have. So in this case, we want to create our beam. So we say, all right, I'm going to name that part beam. And then we have three options. We have a 3D beam. Well, we don't want to go 3D. There's no need for it. We can do it in 2D. We have 2D planar, which of course we said, yeah, we're going to want to do it in 2D. Or there's axis symmetric. Now this one's a little bit different. It's a little bit hard to describe. So maybe I'll describe that one in the lecture, but don't click it. We're not doing it. We are dealing with a 2D planar. Now, if we look at this, we're just going to leave the rest of it. Same with this approximate size. You guys don't really need to care. The only thing that you guys want to define right here is it 3D or is it 2D? Well, in our specific case, it is 2D. So we're just going to click continue. Now it brings you to this kind of this grid line here. It kind of looks like engineering paper. And this is where where we are going to draw our shape. So if we scroll out here, I want to just note to you guys that this grid line here, it actually ends. Oops. The grid line ends. I was getting the shortcuts mixed up over there. The grid line ends. And a lot of you guys may say, Clayton, well, can I draw something outside of the grid line? Well, you can. So don't worry about the grid lines too much there, just to help you if you're doing it up close, but they don't really mean anything. So if we're looking at this actual beam, we know that our beam is essentially just a rectangle. So we have a bunch of options here on how to draw shapes. We have circles, we have rectangles. I can draw a custom shape, so I can define a bunch of points in a line, something like this. But of course, that's not what we're going to do. We want our beam. So I'm just going to erase these really quick because we don't need any of these. So goodbye. We know that we want a beam, which our beam is a rectangle right here. So now, just like AutoCAD, if we were to do a beam in AutoCAD or a rectangle in AutoCAD, we just need to specify the two corners. So I'm going to say, all right, well, the bottom left corner of my beam, let's have that at the origin. So x or y is equal to 0, 0. And as we can see, I have it down here. So if I go enter, I can see that my beam starts at the point 0, 0. And I can click on another point, or I can enter the other point. So this is where the geometry of the beam comes in. We know that our beam is 2 meters long and 0.25 meters in height. But remember, units are very important. As you guys know, I like to keep all of my units in newtons, millimeters. That way, all my pressures will be in MPa, or if I have an MPa and I have millimeters, I know that any forces will be in newtons. So if I want to define the x-coordinate of my beam, which is 2 meters long, I know that that is equal to 2,000 millimeters. So I'm going to say, all right, well, this is going to be 2,000. And the height of the beam is 0.25 meters, which is the same as 250 millimeters. So I enter the other point on the beam, or the top right corner. I go enter, and as we can see, it goes way outside of that little that little grid line. And this is why I'm saying don't worry about the grid line. It does not matter what happens with the grid line as long as you have your shape in the end. And if you guys want to double check it just to make sure it's correct, we have this add dimension tool. So what I can do is I can click it, then I can click a line. And as we can see, it already tells me that my beam is 2 times 10 to the 3, which is the same as 2,000 long. So that's good to go. Alrighty, so this is exactly how we create our parts, and lucky for us, we only have one part. So once we're done creating this part, it says sketch the section for the planar shell. All we have to do is click this button right here that says done. So if I click done here, as we can see, I now have my beam. But it's very important to note that at this point, I may have the beam, but all this is to ABAQUS right now, it's just a shape. It has no properties, anything like that. It doesn't know if this is made of steel. It doesn't know if this is made of concrete. So what we do is we go to our module now and say, all right, well, we have our part done, but we don't have the property defined. So when it says property here, it's basically asking for the material property. So I'm going to go to my module, I'm going to come down, and I'm going to click property. And as we can see here, all of the buttons on the side have now changed. But if we look at our model tree, we can still see our parts and everything else. So it's kind of nice. Now, if I want to create a material in ABAQUS, I use this button right here, this little stress strain curve. So I can either use the button, or like before, I can go back to my model tree, and under materials here, we see we still have that same stress strain curve. So I can double click it right here, and you guys will get this menu right here. And this menu is very overwhelming, but it's actually not too bad. So when it says edit material and it wants a name, this is basically asking you, what do you want to name your material? So for instance, I can call this steel, I can call this concrete. As we know, our material properties that were given, it's basically neither steel nor concrete. So I'm just going to simply call this elastic. As we know, we're dealing with an elastic material, so why not just call it elastic? Now, each one of these titles here, general, mechanical, thermal, these are basically drop-down menus. So if I click general, I have a bunch of different definitions I can give under general. For instance, if I wanted to define the density of the material, I then click density, and right here I can enter in the value of density. However, we're not dealing with density, so I'm just going to delete that really quick. If we're talking about stress strain behaviors, we are going to be looking into this mechanical tab. So if I click mechanical, we see elasticity, plasticity, damage models, and a bunch of other options. But of course, we know that the only thing that we've covered in this course is linear elastic isotropic materials. So I'm going to go down to the elasticity option. From there, I have a bunch of different options yet again, because as you guys will learn later, there's a lot of different types of elasticity. However, we never covered hyperelastic, we never covered hyperfoam. So the rule of thumb with ABAQUS, if you've never heard of it, never seen it, well, you probably don't need it. So we dealt with the elasticity and we dealt with elastic materials. So once I click that, I'm going to have this menu pop up. It's going to say, well, what type of elastic material? So of course we have isotropic, orthotropic, and isotropic. So you guys have covered all of these before, but we know that we're dealing with a nice isotropic material, so we are going to keep that there. And as you guys are going to see, we need to input two arguments in here. The first one is going to be the Young's modulus, and the second one is going to be the Poisson's ratio. Now, luckily for us, that was both defined in the question. So of course, if I'm dealing with a pressure, I want it in MPa, so I know that my Young's modulus is going to be 20,000 MPa. And I'll see if I can scroll this down a bit here. I guess not. I'm trying to make ABAQUS bigger to make the video quality a little bit better, but it's obviously not working too well. But it's fairly easy to see if you inputted it correctly. All right, so we have our Young's modulus is 20,000 MPa. And now for our Poisson's ratio, we had it as 0.2. So I'm just going to go 0.2, and I'm good to go. So now I have both of these defined, and that's all I want for material behavior. I'm not looking at plasticity. I'm not looking at hyperelasticity. Just a nice, simple elastic material. So I'm going to click OK. Now, if I go to the materials option and I expand it, I can see I have my nice elastic material. So far, so good. We go down to our menu and we say, all right, well, I have the part. Well, am I done with the property? Well, I'm actually not done with the property. So here's the first problem a lot of students have with ABAQUS. They define the material just fine, but they don't assign it. So again, right now, if I were to look at this part here, this beam, it's just a shape to ABAQUS. What we do after we define the material, we have to apply it to the shape. So how do we do this? Well, we do this right here with this Assign Sections tab. So if we click Assign Sections, what we can do is we can highlight this beam right here, and we can go Done, and we can assign it a section. Now, once we get to this Assign Section region, we go to our drop-down list, say, hey, Clayton, I don't have any sections to define. Well, this is correct. So after we actually define the materials, we have to define it into a section. So if you guys try and apply the material right away, you guys are going to get this. You're going to have a drop-down menu with no sections, but that's fine because this little button on the side here, this says create a new section, which is what we're going to do. So it says, all right, well, you want to create a new section? No problem. Give it a name. Well, I'm just going to call it elastic because why not? And then we have a bunch of different options. Again, general rule of ABAQUS, if you guys don't know what you're doing, don't touch it. So we're going to keep it solid and we're going to keep it homogeneous. So I'm just going to click continue and say, all right, Clayton, you're doing great. What kind of material property does this section have? Well, this is simply our nice elastic material property. So if I defined more than one material behavior, it would be in this drop-down list here. But of course, since we have only one material defined, we only have the one option. Now, the second option you guys are going to have right here is this plane stress / strain thickness. This is actually important, even though it doesn't look like it. This right here is the thickness of the beam into the page. So we know that our beam is 1 meter into the page, and by default, ABAQUS always sets this as unity. The problem for us, though, is even though it's unity of 1 meter, we're inputting everything in millimeters. So we have to check this option to on, and we have to change this to millimeters. And we know our beam is 1000 millimeters into the page. I can go enter, and now I have my section. So when I'm actually applying the section now to the beam, I have something that pops up, which is elastic, and I go, all right, okay. And if you guys did this correctly, your beam will now turn blue. That's very important. If your beam is not, well, I guess this is kind of greenish. I don't know. I probably sound like an idiot trying to define the color, but your beam will change colors. And you guys want it as this greenish / bluish color. All right. So now we go here and say, all right, well, I created my part. I defined my material property, and then I applied it to my part. Well, the next step is the assembly. So again, going back to Lego, if we define our parts, this is essentially defining all of our little blocks. But now in the assembly, we're going to take all of those little blocks and actually create our model. But again, for us, we only have one part, so therefore we only have to apply one part to the model. And I should probably say how we do this. So what we do now into this assembly option, which is this tab right here, or this button right here, we can say create instance. And what this basically does is this takes one of our parts that we created and puts it into the model space. So I'm going to go create an instance and it says, all right, which part do you want to add? Well, we only have one part created, which is our beam part. So I can go apply. And I say, all right, well, looking good. Oops, sorry, I got to actually click it. And now we actually have our beam inside the actual model. Why is this important that we have to separate the part creation from the model creation? Well, let's say that my model required 2 beams. If I wanted to, I can add a second beam here and do some crazy analysis, something like that. But I'm not going to because, of course, we only have the one beam that we're dealing with. But this is why we separate them, because usually we create all of the little parts in the part module, we give them all properties, and then in this assembly tab, this is where we tie it all together. Now, luckily for us, of course, we only have one part, which is our beam. We are good to go. So for our assembly tab, we actually don't need to do that much. So we say, all right, we are now assembled. We have our beam in the model space. We can move on to the next one, which is step. Now, step's another one that could be really confusing to students, but this is basically the sequence of events that you want to give this beam. So initially, there's only one step. So I'm going to close the assembly tab right here, and I'm going to expand out this steps tab. So of course, we only have one step right now, which is initially, which means what are the conditions of the beam initially? At time is equal to 0, or when all the loads are equal to 0, what is our beam looking like? But we say, all right, well, we have our initial beam, but we want to load it. Now, in order to load the beam, we have to create a step. So you're saying, all right, Clayton, well, what exactly is the step? Well, maybe the name will help you. So in this step, I'm going to say apply load, because this is what I want to do. So the step is actually the sequence of events that you want to do to this beam. Well, I know that what I want to do to this beam is apply a load. So I create a step that says apply load. Now, there's a bunch of different types that we can define the step as. And this goes back to the different type of analysis options, but by default, it will go to static general. And as you guys know from the course, this is what we deal with. But if we were to look at other options, we have dynamic. So we kind of discussed that in the course. And there's a couple other ones. So there's a lot of options in ABAQUS, but in general, we always want to keep everything static and general. So I say okay, and then it's going to give you this big menu here. And this one does look really confusing, but it's actually pretty easy. The only thing I ever recommend doing for this course, it's just turning this on right here, this NLGeom. This is nonlinear geometry, so if anything happens to the model where it undergoes large displacements, this will kind of account for those large displacements. But since you guys have linear elastic isotropic models, you guys shouldn't have to worry about the incrementation or anything like this. Now, I'm going to discuss the incrementation inside of the lecture, but for now, we don't really have to worry about it. Again, when we're creating this, we are just going to click on the nonlinear geometry and click OK. So if I were to look here, I say, all right, well, I have my beam, and then I apply a load. And this is all we're going to do to the beam. We're just analyzing this beam under one load. Let's say I had a more complex analysis. I can add another step that says unload the beam. So unload beam, I say OK, OK, and then what will happen when I'm running ABAQUS, it'll load the beam, and then it'll unload the beam. So this is what the steps basically are those sequence of events. All right, so we say, all right, now we got our step done. Interaction, well, in this case, we don't have any interaction. Interaction occurs when we have multiple parts. Going back to my masonry, of course, I have a lot of bricks stacked on top of each other. So what the interaction module will do is I would have to define the relationship between those two bricks stacked on top of each other. This would include things like friction, stuff like that. But of course, in this one, we don't have any interactions. So we can go to the next step, which is the load. Now, referring back to our nice picture of the beam, we have a single load of 200 kilonewtons, and it's applied at the top right corner of the beam, so where I'm circling the mouse now. So what I'm going to do in my model tree, I'm just going to scroll down, and as you guys see, we have an option here that says loads, but we also have the button right here that says create load. So it doesn't matter if you click the button here or you go down to loads in the model tree and double click it, we can create a load. Now, the first thing that you guys are going to see is it's going to ask for the name of the load. Well, we're just going to put concentrated load, and then it's going to ask you what step do you want to do this in. Now, again, the initial step is just the beam at the very beginning. We can apply loads to its initial point, we need to apply it in step. Well, we know that we actually created a step solely to load the beam. So what I'm going to do is I'm going to switch the step to apply load, and then all of the options become apparent. And this is a great way to know if you forgot to define the step. If you guys forgot to define the step, all you guys will have is the initial step, and you guys actually cannot apply any loads during that initial step. So we're going to have to change this to the applied load step, and we have a bunch of different load types we can choose from. Luckily for us, we know that we're just dealing with a concentrated force, which is the default. So I'm going to click continue. And then what it's going to do is it's going to boot you out into this menu and say, all right, Clayton, what point do you want to apply this at? And as we can see in the corners here, there's little yellow dots. I got my colors mixed up again. And these are the points that we can select from. So of course, we know that we're applying the load at this corner over here. So what I'm going to do is I'm going to go over it. As we can see, that little yellow dot now became highlighted. I'm going to click it to select it. So notice how it stays red. And then over here, I'm going to click done, which means I'm done selecting the points to apply this load. And then you guys are going to get this menu right here. And we have two inputs that we need to do. The first one is CF1 and the second one is CF2. And these are the components of our load. So CF1, this is if we want a lateral load. So if I were to go CF1 and I wanted to, let's say, apply 90 kilonewtons to it and I go okay, as we can see over here, we have a load going in the horizontal direction. But of course, that's not what we're dealing with. So we say, all right, well, I go back to my loads tab. I have my concentrated load that I defined. I can click it and I can edit it. So of course, we're not dealing with any lateral loads. We are dealing with vertical loads. So I go to CF2 and I say, all right, well, I need 200 kilonewtons. But of course, I'm dealing with newtons, so it's going to be 200,000 newtons. Now, the nice thing for ABAQUS is it has that CAD feature in where it shows you what exactly you're doing. So if I go 200 kilonewtons, which is 200,000 newtons, and I go okay, it shows me which direction it's defining the load as. So in this particular case, the load's actually going up. That's because I defined it as positive. Therefore, I'm going to switch that bad boy to a negative, click OK, and now I can see that my load is going in the correct direction. All right, so this is how we create loads in ABAQUS. And we say, all right, well, the model's looking pretty good. I have my beam, I have my material properties inside of the beam, and I have my load. Well, what things am I missing? Well, if we go down to our module and go down, we have load, we have mesh, and we're saying, oh, well, I feel like I'm missing something, Clayton. And you are. So inside of the loads tab, we actually have to do two things. The first one is we apply our loads, but the second one is we can also define our boundary conditions. So the button below that, we have our boundary condition button, or if referring to the model tree, we have this BCs. Of course, this is boundary conditions. Now, since this is a cantilever beam, we know that this whole surface over here is actually fixed. So I'm going to have to actually define that as fixed. So what I can do is I can either click the create the boundary condition button over here, or I can double click the boundary condition on the model tree. And what will happen is this will pop up right here and it's going to say, all right, create a name for your boundary condition. Well, I'm just going to call this bad boy the fixed end. And of course, what step do you want to apply this in? Now, boundary conditions that relate to these displacements, rotations, stuff like that, it's always best to apply them in the initial state of the beam because, of course, the beam will always have that fixed end before we apply any loads to it. So for these type of boundary conditions, best to apply them in the initial step. And what we're going to do is we are going to use the displacement / rotation boundary condition because we know the displacement at the end of that beam. We could also use this one up here, but we're going to talk about that one a little bit later, so don't worry about that right now. This is the easiest to comprehend because you guys are thinking, oh, fixed end. I know I can control the displacement and the rotation, so I can click this one right here. Now what it's going to do is it's going to give you three options to check. U1, U2, and UR3. And this basically means, are you restricting the lateral direction? Are you restricting the vertical direction? And are you restricting the rotation? Now, what you guys are going to see is I'm going to say, all right, well, this is a fixed beam, so I don't want any lateral, vertical, or any rotations, so I'm going to click all three. Now, when we're dealing with these formulations inside of the finite element method for these type of elements, again, these type of elements, as you will see, if you run it like this, you will get an error. Now, the error will say, oh, it's not a problem. We can run it anyway. It's not going to affect your results. But what the error is going to say is you actually don't need to define the rotation. A fixed end beam can actually be defined by restricting both the U1 and the U2 direction in ABAQUS. Now, this goes into the theory of the finite element method. I'm not going to discuss why that is, but I'm just letting you guys know that if you guys want to find that fixed end, you guys only need to click U1 as well as U2. Now, what's nice for us is say, all right, I'm going to define that. And if I look here, it actually has kind of a nice little picture showing that we have a nice boundary condition defined, which is perfect for us because if we look at our model as a whole now, and let's just see if I can get a kind of center it here, I have my beam, I have the dimensions of the beam all correct, I have my material properties all correct, I have my boundary conditions saying that the left end is fixed, and I have my load. And of course you don't see the load because I'm doing boundary conditions, but if I were to click over here on the load tab, we can see our load pop back up. So our load is still there. So the question becomes, all right, am I able to run this? It seems like I have everything from the question. I should be able to run this. So let's look at our modules. If we go down to the next one, we have this one called mesh. Now this is actually the most important one, even though it does not seem like it. So what I'm going to do is I'm going to click mesh, and you guys are going to be booted to this page right here, and you're going to say, Clayton, this looks really confusing. So what I'm going to do is I'm going to show you guys what exactly this is, and then I'm going to tell you guys why we need it. So the first thing that we're going to do is if we go to the mesh module, it's going to say object. And we have two options. We have the assembly or the part. You guys always just want to click the part. So what we're going to do is we're going to take our beam and we're going to apply a mesh to it. And again, I'm going to explain what a mesh is really quickly after I already define it. So what we're going to do is we're just going to click this button that says seed part. Again, I'm not going to go too much what it is, keep the default options. And then the button below it right here says mesh part. So I'm going to click yes. And what you guys will see is your beam will be segregated into a bunch of squares. Now, this is where we start talking about what a mesh is. And a mesh is a collection of nodes and elements. So each one of these squares right here, this is an element. And each one of the corners of the squares, so right here, and right here, down here, these are called nodes. And these are very important because these are how all the calculations in the finite element method are conducted. So what happens here is we see that we have a bunch of nodes. And at each one of these points, these are how the displacements are going to be calculated. Next, from the displacements, if I know the displacements everywhere, I can go inside of this element here and actually calculate those stresses and strains. So that's what's happening inside of the element. So this actually gets very complex. I'm not going to dive too deep, but here's the key takeaway. The finer the mesh, so the more little squares we have, the better the accuracy. Why is that? Because again, inside of these elements, we are calculating the stresses and strains at very specific points. For instance, if I wanted to, I can calculate the stress at this point right here. Now, the problem with me using an element this size is it's going to take that little stress that I calculated right here, and it's going to say that's the same stress for the entirety of this section right here, which we know is not true. So what we want to do is we want to create a smaller mesh in order to capture all the behavior with reasonable accuracy. So we're going to go back to that button that I had before, that seed part button, and I'm going to click it. Now, what it says here is approximate global size. What this means is this is the approximate dimension of your square. So right now it says that it wants all of my squares as 200 millimeters. And I say, all right, well, if we look here, that was actually pretty big. We should probably have it a little bit smaller. So how about we make all of our squares 20 millimeters? And we say, all right, switch that to 20. I can apply it. And this is going to say, hold on one second. You already created a mesh. Are you sure you want to delete it? Well, yes, we are sure we want to delete it. So I'm going to click that, delete mesh. And now we can see that our seeds over here are much smaller. What does this mean? Well, if I click the mesh part again now, okay to mesh the part, yes it is, we have a bunch more small squares, which is great because if I calculate the stress at this point inside of that element, well, that stress only applies, sorry guys, that stress only applies to this little region right here and not the entirety of this region over here. So the key is trying to find a good balance between mesh and accuracy, because as you guys will see, if I want to use a very, very tiny mesh, let's say I go into here, I define my mesh size as 1, I go okay, and then I mesh that part. As we can see, there are so many little squares. Now, the problem with each one of these squares is each one of those squares is a calculation. So the more squares I have, or the more elements I have, the more calculations I have to do. It's going to take your computer forever to do it. So this is where we have to find the nice balance. So I'm going to go back to 20. That didn't look too bad. It looks actually a little bit dense, but this one will capture the behavior reasonably well. So this is very important. If you guys don't define the mesh, your model won't run because you haven't defined any spots to actually do any calculations. You basically just gave ABAQUS a shape and said, play with the shape. Of course, ABAQUS doesn't know how to do that. It knows how to calculate things. In order to do that, we need to go into the mesh option. And at this point, we are good to go. Because if we look at what's after mesh, it's optimization. Again, I've actually never even used this. I don't know any idea when you guys would ever use this, so don't worry about that. We go to the job module. Now, the job module is the best part because it's actually really simple. This basically says, I want to run this analysis. So what we do here is we can go right here that says create job, or down here, we have the jobs button. I can double click and it says create job. So I'm going to call my job, let's just call it analysis 1. Source the model, so it's going to take whatever model you currently have, and we're going to click continue. Now, here's all the computational part. Again, if you guys don't know what this is, don't touch it. So we're going to change absolutely nothing in this job. We're going to keep it all default. And when we do that, you can see that we actually create the job analysis 1. Now, the analysis hasn't started yet. We just have the analysis created. So in order to run our analysis, what we do is we come down here, we right click it, and we click this submit button right here. All right, guys, so once your guys' analysis is complete, just like what we did to start the analysis, we can right click it, but instead of going submit, because we don't want to run the analysis for a second time, what we do is we come down here to results. So after we click results, we're booted to kind of what looks like a different menu, and these are the results of our beam. So right now, by default, it's going to give you the beam in its undeformed shape. So here's kind of the key here. Right now, it's undeformed. The load has not been applied yet. If you want to see the effects of the load, what we do is we click this button just down below it, which says plot contours on the undeformed shape. So if I just wanted the undeformed shape, I can click this button over here. And as we can see, the beam kind of bends down a little bit. If I click them back and forth, you guys can kind of see what's going on. But if we want to analyze the stresses and the displacements in the beam, what we do is we want this one down here, this nice colorful one, kind of looks like an RGB keyboard. We click that bad boy. And as you can see, we are now given the von Mises stress distribution over the beam. This is given because it says S, comma, Mises, so it's saying the von Mises stress distribution throughout the beam. And if you guys remember from your assignment that you guys did in Mathematica, this looks very similar to the kind of the plots that you guys were generating, which means that you guys were on the right track. And even though you guys don't know the finite element method, you guys can probably get a pretty good approximation from this using the theory that you guys do know. Now, some of you might be saying, you know what, Clayton? I don't give a rat's ass about the von Mises stress. What about the displacements? That's a great question. So what we're going to do is we go to this tab up here. Now, this one could be located maybe over here for some people, but basically you're going to get a tab that says primary, S, and then Mises. And these are the things that we're going to want to change. So this S right here, this means stresses. The second tab next to it is the kind of stress that you want. So let's say that I didn't want the von Mises stress. I can click on it, and I have a bunch of different options for different values of stress. I can see the plot of sigma 1,1 throughout the beam. I can see the plot of sigma 2,2 throughout the beam. I can see the plot of sigma 3,3, but of course we know that this is 0, therefore not much of a plot, but we can see it if we want it. But again, you guys might be saying, you know, I don't want the stresses, I want the displacements. Well, what I can do is I can click the S, and instead of stresses, I can go down to U, which is the displacement. So I click here and I have a displacement profile of the beam, but it's important to note that by default, it'll give you the magnitude displacement. Well, we don't really care about that. We want either the horizontal displacement, so I can click that to get my nice horizontal displacement, or I can click U1 to get my vertical displacement. Now, if we look here, it says at the very end of the beam here, and the best way to actually figure out these exact values is coming down here to this button right here. It says probe, which is exactly what we want to do. We're going to violate this beam with a probe. And what we can do is we click nodes over here, and then we can click it on the point that we want to analyze. So as we can see here, as we hover over the beam, it gives us the values at different points. Well, if I want to analyze the point where I applied the load, I can simply click on it. And it's not too easy to see, but it says that our displacement here, and actually I'll just keep the mouse over it, our displacement there is negative 20.97 millimeters. And if you guys are wondering how this approximation fares to the theoretical value you guys get from continuum mechanics, well, if we calculate it, we'll get that this beam displaces 20.48 millimeters. So the answers are actually very, very close. Now, some of you guys might be saying, hold on, Clayton, I don't care about very close. I want almost exact. Well, the problem is you guys are not going to get almost exact. And the reason why is because of this. If we go back to our model by clicking the model tab up here, and we go to our properties, we defined the Poisson's ratio. Now keep in mind that this Poisson's ratio is not accounted for when we did our analysis. So in actuality, ABAQUS's answer, I would actually say that's more accurate than the answer we calculated in the theory because we are accounting for this Poisson's ratio. Now, with that being said, we actually can increase the accuracy of the approximation. So keep in mind, ABAQUS is just an approximation, and we can increase the accuracy with the cost of computation time. So you guys think, Clayton, I have a supercomputer, it's good to go. I don't care about computation time, I care about accuracy. Well, good for you. This is how we do it. Just like before, all of these steps, well, they're just creating the models. So we're going to have nothing to do with these. We're going to go into mesh because keep in mind that mesh, this is how we define where all the calculations are done. So we go back here and what we see is we have our beam mesh. Again, it's pretty fine. And you say, Clayton, I've already made the mesh very, very fine. How else can I increase the accuracy? Well, what we can do is we can change the element type. So right now, by default, ABAQUS gives us a 4-node linear element. So if we look over here and we look at this element right here, this square, we see that we have a node at each corner. So in total, we actually have 4 nodes. But what we can do is we can say, all right, well, I can have an 8-node element. What is an 8-node element? Well, basically, it does more calculations. So in order to change that, I can go to this S4R where it says assign element type. I can click it, and then I get this menu right here. And this menu is the key to increasing your accuracy if you guys want. The first one that I recommend doing if you guys want to try higher accuracy is remove the reduced integration. In order to calculate the stresses and strains, of course, we integrate, but being an approximation, ABAQUS doesn't really integrate. We use Gaussian methods. So this will actually improve the accuracy of that method if we uncheck this. So just by unchecking this, we'll start increasing the accuracy. The other thing we can do is we can modify the geometric order. So right now we have 4-node elements, which are linear, but we can change that to 8-node elements, which are quadratic. So what I can do is I can click quadratic and say, all right, looking pretty good. And again, it'll default back to the reduced integration, but I say, you know what, I don't want the reduced integration either. I want this as accurate as possible. I can click OK. Now if I look at this beam, as you guys can see, I have an element both at all 4 corners, but then at all of the midpoints right now too. So instead of just calculating the displacements at each one of the corners, I'm also calculating the displacements kind of in the middle of each element, which makes a big difference if you guys start getting into nonlinear materials. This is a linear elastic isotropic model, so it's actually not going to change things too much. So let's say that you made the changes you guys want to do. All you guys are going to have to do is go back to your analysis, which is completed, but I can right click it and I can submit it again, which is saying, oh, hold on, you already did an analysis. Do you want to overwrite it? Well, yeah, I don't care about my previous one. I want that higher accuracy, so I can go submit again. And as you guys will see, it'll go submitted. So at this point right now, it's just taking all of the information in your model, converting it into a file. Once it does that, it starts running the analysis. And then after that, it'll say complete, which means that the model ran successfully, and we can right click it and go results. So now just like before, I can click the deform shape and we can see kind of what's going on. But if I want the contour plots, I go down below, click it, get my nice contour plots. What I can do is I can say, all right, well, I'm interested in that vertical displacement. So I go U and then U2. And as we can see down here, it's now at negative 20.8 millimeters. So it got a little bit closer to the theory, but it's still a little bit higher. But again, this is expected because keep in mind that this analysis right here, this accounts for things like Poisson's ratio, things that are typically neglected when we talk about the theory in continuum mechanics. All right, guys, so this is kind of the first ABAQUS tutorial. I know it's a little bit longer. I just wanted to kind of explain each step in a little bit more detail. After you guys know all these details, the next examples will actually be a lot quicker because I won't have to go in depth, as much in depth on each one. So thank you guys all so much for listening. I'll see you guys in example number 2.